Okay, so today we're talking about domain, range, and rates of change. And that's section 3.2 and 3.3 in Edfinity and in the textbook. So we previously talked about the idea of domain and the idea of range, but we'll be introducing the notion of rates of change. Okay, so what do our learning objectives look like today? Well, first off, we're going to talk about how to find the domain of a function given an equation for the function. So we'll talk a little bit about how to find the domain and range just from the graph. It's just the set of all possible x values and the set of all possible y values, the x values being the domain and the y values being the range. But we have to think a little bit about what happens when we're given just an equation for the function. Then we'll talk about the notion of piecewise defined functions. And those of you going on to calculus, this is one of the most difficult concepts for students in calculus. So it's a great idea to have a solid understanding of it here, where we're not talking about any sort of calculus at all. We'll introduce the notion of the average rate of change of a function. The average rate of change is sort of a measure of how much change is happening. Is the function going up? Is it going down? And by how much? And we'll use the idea of slope and the average rate of change to define that. And leading to those, we'll introduce the idea of increasing and decreasing and what it means for a function to be constant. And that'll nicely lead into the notion of a maxima and a minima and the difference between local and absolute. So we'll be introducing those last two sort of at the end of the video. If we can't quite get all the way through those last two by the end of the video, we may have to talk about it on Monday during our review session. I'll make a really short recording, maybe about 10 minutes or so to finish those two topics up if we don't get there. And then that means the quiz that week on Monday will be a bit shorter than normal. But we'll just see how far we get. And my last class, I made a slight error. We had to go back and redo a problem, and that slowed us down by quite a bit. So we didn't quite get there, but we'll see with this one. I know there's a lot here. So I'll give you guys a few moments to write it down. And then once you have it written down, if you're writing it down, give me a thumbs up. And as soon as we have enough of those, we'll go on to the next slide. Okay, so it looks like quite a few of you are done. So we'll go ahead and move on to this first objective, okay? So we'll do some examples where we talk about domain and range in terms of graphs. But here we're going to talk about domain and range in terms of an equation. So the picture you should have in mind is that the domain, again, is the set of all inputs. So these are the things that you could throw into your machine. And then the machine has some sort of equation or some sort of description in terms of a table or a graph or something like that. And you can use some process to then figure out what the output of your given input is. And the set of all outputs, or the collection of all outputs, is called the range, and the inputs are called the domain. And today we'll be focused on sort of describing what the domain of functions are. The next guy here is just a reminder of some interval notation. So I don't expect you to go through and write all of this down. I think we had this in a previous video. So it's just telling us what we had already covered in terms of intervals. And the point of bringing this up, just as a quick reminder here, is that the domain will typically consist of infinitely many different real numbers. And so we'll have to express the domain in terms of an interval. Right? So many of the times when we look for the domain, we'll express the domain in terms of an interval. And furthermore, when we start talking about piecewise functions, we're going to break up the domain into several different pieces and use a different formula in each piece. Okay? So this is just a reminder here of this idea of interval notation. Remember, the bracket means you include, the parenthesis means you exclude the value. Okay, and we'll need to sort of solve some inequalities, right? So that's why the domain will naturally sort of be in this format of an inequality, of an interval. Okay, so what do we have to be worried about when we're finding the domain and range? And this really is a question about the domain and range when you're given the function in terms of an equation. So like, for example, the first one we'll look at is the function f of x is equal to 5 times the square root of x plus 2, okay? And let me go ahead and show you that function. So this is the first function we'll look at. This is what I mean by functions defined by an equation. It tells you, you plug in x, and then to go through the machine, you add 2 to x, you then take the square root of whatever that is, and then once you've taken the square root, you multiply by 5. And that's the output of that particular x. So that will be that process of going through the machine. And here the question is, what values of x can we actually plug in and obtain something that's a real number on the output? Okay, so before we answer that, let's come here and talk about the how-to, okay? So your first thing that you have to be worried about is possibly dividing by 0. If you plug in a value into the input of a function and it results in you needing to divide by 0, then you have to exclude that value from the domain. So you sort of answer this question in reverse. You assume that everything's in the domain, and then you go step by step and remove things from the domain. And here this first one is telling us remove anything that results in division by 0. So we have to be careful about dividing by 0 because we just can't do it, right? It doesn't make sense. The next thing that we have to be careful about is taking the square root or the even root of a negative number. And what that will give us back is a non-real answer. It will give us a complex number, like an imaginary number, like the square root of negative 1 is not a real number, but a complex number. And here when we're talking about domain and we're graphing things in the xy plane, there's only real numbers, right? We don't have any complex numbers floating around in that picture. So we need to make sure that we're not taking the square root of a negative number. But we also need to make sure that it's not just square roots, it's even roots, right? Anytime the index there is even, like a 2 or a 4 or a 6, we need to worry about this. If it's a cube root or an odd root, right, like the 5th root or something like that, then you can plug in positive or negative numbers. There's no issue, and you'll get back a real number. So it's only the even ones, that even roots that you have to worry about. And then here, we then use those values to determine the output values. So these first 2 steps will tell you the domain, what you exclude from the domain, and then you'll use that information to determine, okay, what's the actual output? And then finally, they suggest, graphing it on some sort of graphing calculator or maybe online somewhere. There's lots of nice graphing calculators online for free, and just checking to see that it matches up, with what you expect graphically. And we'll talk about here in a moment how to find the domain and range graphically. It's much easier than this. Okay, so let's come back to that example. And I'm going to call this example 1. And here we want to find the domain. And if we're following that process, the first thing that we have to do is be worried about dividing by 0. But you'll notice here that there's no divisions at all, right? So we're not dividing by anything, and so we can just bypass that step. We don't exclude any real numbers in that step. However, we do have a square root here, and because we have that square root, whatever is inside of this even root has to be greater than or equal to 0, right? It can't be negative, because if it were negative, we get a complex number. So here, to be in the domain, you have to be you have to satisfy the following inequality. X plus 2 has to be bigger than or equal to 0. Okay? So we're rewriting the question about finding the domain as an inequality. And now we want to solve the inequality. We want to find the set of all x values that make this true. It's pretty straightforward. You just subtract 2 from both sides. But remember, you may have to use something more sophisticated because something under here might be quadratic or something more complicated. And you'll have to use your techniques from chapter 2 to solve these inequalities. So there may be a compound inequality or something like that showing up here. Okay, so in the chat, tell me what is this in interval notation? How would we write this in interval notation? All the numbers bigger than or equal to -2. What does that look like? And once you have it, put it in the chat, and we'll go from there. Okay, so again, this is any x which is bigger than or equal to -2. So yeah, we should include the -2. So we put a bracket there on -2, and then we just go all the way out to infinity. We don't include infinity because it's not a real number. And this determines the domain. These are all the things that you could plug into this function. Anything to the left of -2 you can't plug in, right? You get a complex number, so it wouldn't even be on our graph. Okay, so this is the domain. And if we're following the how-to, we should also find the range, even though it's not part of the question here, but let's think about what the range is. And what happens is you plug in these values, and the smallest one that you would get is this -2, right? So if I plugged in -2, I get -2 plus 2, that would be 0. The square root of 0 would be 0, and 0 times 5 is 0. So if I plug in -2, the output of this function is 0. Now, if I plug in anything else in this domain, then it's going to be the square root of a positive number, which is positive. So that's even bigger than 0. So in other words, the range is all non-negative numbers, right? Anything bigger than or equal to, that's why I put a bracket there, 0. And that makes sense because this function is never going to give you a negative value, okay? In this case, we didn't really do anything with the 5 here because we were just thinking about what's the smallest value, and then as we plug in bigger and bigger values, this just gets bigger and bigger, right? So any value in between 0 and infinity, we can pick out if we would like. The more important part of this problem here, though, is the domain, right? So typically, we'll be more interested in the domain. But the answer would be the same if there was a 5 or there's not a 5, whatever constant you have out in the front. Okay, so that's just following these guidelines here, and we're talking about number 2, excluding from the domain anything where you're going to get a non-real output. Okay, but we skipped by 1, so let's talk about how to deal with number 1, and that's when there might be a division by 0. So let's change this problem slightly and talk about a rational function. Okay, and this rational function here is going to be x plus 1 divided by, and I'm going to factor it for you down here so we don't have to really think about factoring, but it may be given to you sort of foiled out, x minus 1 and 2x plus 1. Okay, and here you'll notice there's no radicals or square roots. So we don't really have to be worried about taking the square root or the even root of a negative number. All we have to do is be worried about what happens if the denominator is 0. Okay, what happens if we're going to divide by 0? Okay, and the how-to says we need to exclude those values. So here we need to make sure that x minus 1 is not 0 and 2x plus 1 is not equal to 0, right? So that's what we're doing when we follow step 1. We're saying, okay, what makes the denominator 0? Well, it's either the first factor, x minus 1 is 0, or that second factor, 2x plus 1 is 0. Okay, so in the chat, tell me what should we exclude for this one, and what should we exclude for this guy here, right? What are the 2 values that we need to remove from the domain? Okay, so this one is going to be 1, so we just add 1 to both sides. And if x is not equal to 1, right, because we can't plug in 1 for this piece here. If we did, we would get 0. So we can't plug in 1. And then this one over here, we subtract 1, and then divide by 2. And so we get negative 1/2. Okay, so those are the 2 that we need to remove. And let me draw you a picture here of what's going on, because these are the ones we remove, right? So let's say here's our number line. Here's 1, here's 2, here's -1, here's -2. We would need an open circle at 1 to show that we're excluding 1. Okay, we did not include 1. And then we would need an open circle at -1/2. So -1/2 is halfway between 0 and -1. So that's here. And those are the ones that we're excluding. So it means we include everything else. So we include this region from here to here, and this region out to the left, to the right, and this region out to the left. So there are sort of 3 regions here, right? The first one is from -infinity all the way up to -1/2, and we exclude the 1/2, so we put a parenthesis there. The next region that we have is the region between -1/2 and 1. So that's the region between -1/2 and 1, and we exclude both of those endpoints. And then finally, we have this region from 1 all the way out to infinity. And the way that we glue them all together, and how we'll have to answer an infinity, is by putting a U, or a union symbol. And that means just glue those three regions together. So the domain in this case in interval notation would look like this. Okay? To write it as three different regions and then union them back up. And again, it's because these are the values we can plug in. These are the values that we can. Right? So we have to write it out in this format. Okay, so those are the two basic things that you have to worry about: division by zero and taking the square root of an even root. And they could come together, right? It could be like something like 1 over the square root of some even root. So you have to think about sometimes both those things together. Okay, so let's now go on and talk a little bit more about how to do this graphically. So remember, we talked about how we can define a function. A function is just a collection of ordered pairs, and therefore a graph, right? Just a line in the plane. It's just a collection of ordered pairs, right? So this blue line you're seeing here is a function. It's a collection of ordered pairs. And the way that we know it's a function is if it passes the vertical line test, right? Every vertical line intersects the graph in at most one place. So there are two different types, right? There are the ones where you intersect the graph in one place. For example, here at -2, if I go at that vertical line, at -2, I intersect the graph in one spot right here. Same thing at -4. I intersect at one spot right here. At -5, I intersect right here at one spot because there's a closed circle. If it was open, I wouldn't intersect at that spot. However, if I draw the vertical line at -6, you notice I never hit the graph. Same thing if I draw the vertical line at 5, okay? So if you, let me see if I can remove this little piece down here. Okay, so if you look, came back. But anyway, if you look at the picture when that was gone there, then you'll notice that this vertical line here never hits the graph, okay? So this vertical line never hits the graph. And the distinction between those two types of vertical lines tells you what the domain is. If you hit the graph in one point, then you're in the domain. And if you don't hit the graph, then you're not, right? So for example, -6 is not in the domain, but -5, -4, anything in between, all the way up to 4, and as close as we get to 5 are all in the graph, right? Are all in the domain, but the range, are all in the domain, but 5 is not, right? So the domain here starts at -5 and goes all the way up to 5, but it doesn't hit 5, right? It doesn't include 5. So those are all the vertical lines, the x values of vertical lines that hit the graph. So in terms of interval notation, what is the domain of this graph? How would we write that in interval notation? So the smallest value of x we're seeing is -5. The largest value of x is 5. But what are the endpoints? Do we include or exclude -5? And do we include or exclude 5? And when you have it, post it in the chat. So we certainly should include -5. And that's because if I looked at that vertical line again, that is going through -5, it intersects the graph at that closed dot. However, if you look at the vertical line here, the one where that circle is at, the one going through 5, it does not hit the graph. That's called a vertical asymptote. And so Dalton has the correct answer here. We have to exclude the 5, okay? Because the vertical line there never hits it, okay? We only include x values of vertical lines that hit it. And that's because that's how we evaluate a graph like this, right? If I wanted to figure out what the output was at 4, f of 4, I would go boom, hit the graph here, and I'd say, the output was -3. At 5, I can't do that. I just go down to the graph, and I never hit the graph, so I don't know what the y value would be. So it's not in the domain. So in this case, it's -5 to 5. And when we're dealing with the range, we do the same analysis, but now with just the y values, okay? So here, the largest y value is 5. And then as we go down, the y values go from 5 to 4 to 3 to 2 to -1, and they just keep going on forever. So this was the domain, and the range starts out at 5. Goes down from 5, including 5, but it goes all the way down to negative infinity, right? We hit every y value as we go down. That's what those two arrows going down forever mean in that picture. So the domain are the x values in the graph. The range is the y values in the graph. Okay? And be careful about closed and open circles because they tell you if you include or exclude a given endpoint. Okay, so that's domain and range graphically, and we'll talk about a couple more examples of this sort of at the end of class. But what we now want to do is skip to the next learning objective, and that's this idea of a piecewise defined function. Okay, so again, these come up fairly often in calculus. They're often sort of one of the more difficult parts of the class for students because they didn't really pick them up in college algebra or in their previous courses, and they have to learn them again. So this is a really good one for you going on to calculus, those of you going on to calculus to pick up now, right? Because there's no calculus you really need to understand it. It's just a question about domains. Now, those of you who are not going on to calculus, for example, maybe those of you who are in a nursing major, I'll just point out that functions like this show up all over the place in medicine, especially when you're injecting drugs and looking at the concentration of the drug in the bloodstream, right? As you inject, you get a different domain and a different equation, and so they come up fairly often in different spots, okay? So it's not just calculus students that will see them, but it's really important for them to understand that. Okay, so how do they work? They're called piecewise functions, and what we do with a piecewise function is we break up the domain into a bunch of parts, right? Into a bunch of different pieces. So we might have 3 pieces, like in this equation here. So here's the first part of the domain, if you're in the second part of the domain, or the third part of the domain. And in each different part of the domain, you use a different formula to calculate the output of the function. So that's what this big bracket means. If you want to compute the output of the function, the formula you use depends on which portion of the domain you're in. And the typical or the sort of prototype example of something like this is the absolute value function, right? It really is a piecewise defined function because the way that it works is you use 2 different equations when you want to compute the absolute value of a positive number and when you want to compute the absolute value of a negative number, right? So you do 2 different things when you compute the absolute value of a positive and a negative, right? And so, for example, when you have a number that's bigger than or equal to 0, if you compute the absolute value, you just get back x, okay? So, for example, if it's 2, the absolute value of 2 is just 2. If you had something that was negative, for example, negative 2, then you get back the negative of that value. And so what they mean there is that you get negative, negative 2, and a negative, negative gives you back the positive value, right? So you're using a different formula depending on which portion of the domain you're in, right? And really the absolute value function is sort of the prototype example of this sort of thing. And things can get more complicated. So let's look at another example, the type of thing you'll see in affinity. Okay, so affinity will give you a function that's defined piecewise like this, and they'll ask you to compute the range in the domain. And what you need to do is graph it, okay? So with lots of these, it's going to be best if you just actually graph it. And there's not a graphing calculator you can type this into, so you'll have to actually just graph it by hand. And the first thing that you want to do is you want to think about how the domain is broken up. So here there are 3 different pieces in the domain, and I'll color them in the number line here in a moment. There's the piece where we're smaller than 1, so this is x is less than 1. There's the piece where you're between 1 and 2, but you could be equal to 2. And then there's the piece where you're bigger than 2 and certainly not equal to 2, okay? So let me draw that here on the board. There are sort of 3 different regions here, right? So here's, say, 0, here's 1, here's 2, and then the graph goes on in that direction over there and in this direction over here. The first region that we're looking at are the things that are less than or equal to 1. That's the first part of our domain, okay? So the things that are less than or equal to 1. So here's 1, and we want to look at the things that are less than or equal to 1. So I'm going to put a big orange circle here, say we include 1, and then we look at everything less than 1. Okay, so that's that region there. And that's the first part of our domain. Now, the second part of our domain here was this second region, and it's the numbers between 1 and 2. You don't include 1, but you include 2. Okay, so let's come back and draw that on our picture here. So it's the numbers in between 1 and 2. You don't include 1, and you do include 2. So it would go between 0 and 2, and then a big yellow closed circle there. Right? That's the different region. And then the last one I'll do in blue. The last one were the things bigger than or equal to 2. Not equal to, but bigger than 2. Okay, so coming back to this guy, that means that you're just to the right over here. So I'll put that region in blue. And you don't include 2. Okay? And in each one of these regions, if your input value is in one of these 3 different regions, you use a different formula. For example, in that first region there in orange, the formula that you're going to end up using is x squared. So it looks like a parabola in that region. If you're in between 1 and 2, you're not even going to use a formula at all. You're just going to get a constant value of 3, no matter what. You always get 3 in this region here. And then finally, in the final region, when x is greater than 2, the output is just x. So just like the absolute value, right? So once you get to a certain spot, it just outputs the same value as you input. Okay, and let's try to graph this, okay? So to find the domain and the range, the domain is going to be pretty easy, but the range is going to be the harder one, and we'll need to graph it in this case. You'll want to think about it in 3 different pieces. Okay, so these are the 3 different pieces of the domain and the graphs that show up. And we saw each one of these graphs in the last lecture as our sort of toolkit of functions. So the first one here is things less than 1, right? So this is the domain, and there were the parabola x squared. And to get the points on this, you just plug into the formula. For example, -2 is less than 1, so you use that formula for x squared. -2 squared is a y value of 4. So we get a parabola in this region, which is less than or equal to 1. In the region from 1 to 2, we have an open circle here because we're not equal to 1, and we got a value of 3 between 1 and 2, including at 2. Okay, that's why we have a closed circle there at 2. And then finally, in that third region, when we were bigger than 2, right? So bigger than 2, that's this region over here. We were the line, we were the function f of x is equal to x, right? So here was that, sorry, come back to it. Here was that value, it was just x, right? So it was x squared in this region here, 3 there, and then finally x there. So here, when we plug in 2, we get an output of 2. When we plug in 3, we get an output of 3. When we plug in 4, we get an output of 4. We just get a line with slope 1. And those are the 3 different regions, right? And we have to restrict our domain. We don't want to include anything else in these graphs because we've restricted our domain to these 3 parts here, right? Now, to graph the piecewise function, you put it all together. And this is what it looks like, okay? This is the one function that's described by that piecewise function. When you're less than 1, you look like a parabola. When you're in between 1 and 2, you look like a horizontal line. And when you're greater than 2, you look like this line, y equals x. And you can now use this information to find the domain. The domain, you can plug in anything, right? If I draw a vertical line, I'm going to intersect this graph in 1 point everywhere. So the domain in this case, for this function, is -infinity to infinity. There's nothing we're restricted to plugging in. And then the range, we have to be a little bit more careful about. The smallest y value that we see is down here at 0. And as we go up this side, we get y values of 1 and 2 and everything in between, okay? So here, all of the y values from 0 out to infinity appear on the graph. So in this case, that means the range is the region from 0 to infinity. Okay? So you want to graph it first, and there's about 6 or 7 problems like this in Infinity, right? You want to graph these guys first, and then think about what that domain and range look like. Okay, so that's it for, I think, piecewise functions, what I wanted to say. And on Monday, you can ask some more questions about those guys if you need some help graphing those piecewise functions. And we're ready to move on to the next topic here. So the next thing we're going to look at is what's called the average rate of change. And again, the average rate of change is a way of measuring how much change the graph is undergoing in a given interval, okay? So we're going to be looking typically at the interval between x1 and x2, okay? So for the most part, in all of these problems where you're asked to compute the rate of change or the average rate of change, you will be given x1 and x2. You'll also be given the function f of x, okay, the formula for f of x, and then you have to just go through and simplify this. So let's try and understand what it means and why they're using this change in y over change in x, right? So that's a delta y, the Greek letter delta, and then the Greek letter delta x on the bottom. And that's read change in y over the change in x. Okay, so let me just draw you a picture of what's sort of going on here in the abstract. You may have just some arbitrary function. Let's say it looks like this. This is y equals f of x, and we're given two values, say down here. I'm going to call this one x1, and it goes to this point right here on the graph. And then I'll pick x2 over here, and it goes to this point here. Okay, and x2 is typically the larger one, and x1 is the smaller, but it doesn't matter as long as you're consistent with what you choose for x2 and x1. And if it's a function, there's only going to be one point on the graph above these guys, right? Because it's going to pass the vertical line test. And so there'll be a unique point here, and there'll be a unique point here. And the average rate of change is going to tell you how much change this function has undergone in between these 2 points. And the way that you measure that change is you draw a line between the two of them, and you look at the slope of this line. Okay? And if that slope is negative, it means that the graph was going down. And if the slope was positive, it means that the graph was going up, right? And the more positive it is, the more it was going up, the bigger the change. And if it was more negative, like negative 1,000, the more sort of vertical it would be as well, and it would have a bigger change going down. So the slope of that line is telling you sort of a measurement of how quickly the function is changing. Okay, so coming up from x1, if we come back to the y-axis over here, this is going to be f of x1. That's the output of x1, okay? And this guy over here, we're going to come back to the x-axis, and we're going to get the output f of x2. So this distance from here to here is just the difference between the two of them, f of x2 minus f of x1. Okay, and this distance from here to here is the distance between, or the distance between x2 and x1 is x2 minus x1. So this distance from here to here is x2 minus x1. And this one up here was f of x2 minus f of x1. And so the change in y over the change in x, that's the slope, the rise over the run, is just going to be this distance here, so that's f of x2 minus f of x1, divided by this distance from here to here, the run, x2 minus x1. And this computation, this value is called the average rate of change, okay? So you can do this for an arbitrary function. Typically, they'll give you the formula for your f of x, okay? But this is what's going on graphically, and it's what's measuring. It's telling you when the function goes down and when the function goes back up, okay? And by how much. Okay, so let's do a few examples of using the formula, because it does show up a lot in the homework, and it will show up in calculus for those of you going on to calculus, probably in the first day of class. Okay, so just a quick example where we give numbers, and then a quick example where we're given variables. So in this case, let's find the average rate of change of f of x is equal to negative 2x plus 1 over the interval from 1 to 3. Okay? And here they're talking about x values. Okay? So this is going to be your x1, and this is going to be your x2. And it doesn't matter how you pick the x1 and the x2. Typically, I pick the x2 to be the larger one, but as long as you're consistent with what you choose, you can pick whatever you'd like, right? So I'm going to call that one my x2. I'm going to call this one my x1. So it's telling me along the x-axis between 1 and 3 what's happening. And the number we're going to compute, if it's negative, means we're going down, and the more negative it is, the more vertical it will be. And if it was positive, it would mean we're going up, and the more positive it is, the bigger the slope up, okay? So that's what we're computing here for this function. Okay, so the change in y over the change in x is going to be f of x2 minus f of x1, which is 1 here, divided by x2 minus the x1. Okay, I'm just plugging in x2 and x1 into that formula that I had up for the average rate of change. Okay, so now we can use the formula to compute f of 3 and to compute f of 1. Okay, so in the chat, compute f of 3 for me, and post your answer. What do you get for f of 3? Okay, so -5, and that's because -2 times 3, that's -6. -6 plus 1, that's -5. Okay, so f of 3, we're just using the function to evaluate. What about f of 1? What happens when I evaluate this function at 1? Okay, if I plug in 1 here, I get -2 times 1, so -2, plus 1, that's -1. But notice there's a negative here. So you have to be really careful here. It's going to be negative or minus -1, right? So you're subtracting -1. And then on the bottom, we have 3 minus 1, which is just 2. So up here, this is -5, and a minus minus means plus 1. So we get -4 over 2. We get -2. So the average rate of change between 1 and 3 is -2. And that means that the graph is going down, right? The graph is going down. Well, we should have expected that. This is the graph of a line. This is a line with slope -2. So yeah, when we compute the slope, we should have expected to get -2. But the functions won't always be lines, right? So you can do the same sort of computation even when the function is not a line. And furthermore, the book will ask you to do this when these are variables as well. So not just numbers, but sometimes you may get a variable. So let me go ahead and do an example along those lines. This is going to be number 4. And for number 4, we want to find the average rate of change of the function f of x is equal to 2x squared. And now we're going to go over the region from 4 to 4 plus h, right, where h is a variable. So this is what I was saying before. Sometimes they'll make your x1 and your x2 another variable altogether. And there are a couple of examples like this in Affinity, and also this is how you'll sort of see it when you get to Calculus 1, right? So I'm going to call this guy my x1 and this guy my x2. And it's easy to flip the x1 and the x2, right, to plug them in sort of the wrong way or something like that. So make sure that you're consistent and you mark them down at the very beginning. And then the change in y over the change in x, it's going to be f of x2 minus f of x1. And then on the bottom, it's going to be the same thing. x2, 4 plus h, minus x1, which is 4. Okay, and the h is just going to be part of the answer, right? So now in Affinity, they'll tell you, okay, multiply this out and simplify. And they often will call this the difference quotient, right? It has a name. The textbook doesn't name it, but Affinity does. They call it the difference quotient. So if you see that terminology there, that's all it means. Down here, the 4 and the -4 cancel. And up here, we'll plug into the formula. So everywhere we see an x, we plug in 4 plus h. 2 times 4 plus h squared minus. Here, everywhere we see a 4, we'll plug, everywhere we see an x, we'll plug in a 4. So this is just 2 times 4 squared. And then all of it, the 4 is canceled, is divided by h. Okay, so this we have to multiply out. So let's start by FOILing this out. What is 4 plus h squared? What do we get when we FOIL that guy out? Remember, it's 4 plus h times 4 plus h. Okay, so again, as soon as you FOIL this guy out. All right, yeah, so we're going to get 4 times 4, that's 16. And then there's a 4h times a 4h, so 8h. And then an h times h, so h squared. And then what's the 2 times 4 squared? What do we get for this one? Okay, 32. All of it divided by h. Okay, now we can distribute the 2. So we get 32 plus 16h plus 2h squared minus 32, all divided by h. And that's a division by h there. Okay, so now this 32 cancels with this 32, and I'll move right over here. And we get 16h plus 2h squared divided by h. And we can simplify, right? In infinity, they're going to ask you to simplify this. So here we'll factor the h out, and we get 16 plus 2h. That h is getting factored out, and we cancel it out. And we're left with 16 plus 2h. And that's the average rate of change between 4 and 4 plus h, right? And it depends on h. If you change the value of h, you're going to get a different value for this average rate of change. Okay. So this is probably the most difficult stuff you'll see in this section on rates of change. And it's when you have to plug in variables here on the endpoints. But all you do is you plug into the formulas and you simplify as much as possible. Okay. So those were the 2 examples I wanted to do of rates of change. Let's go ahead and come back now and finish up the last couple of objectives. Because I want to talk now about what did the average rate of change tell you? Well, the average rate of change told you basically when the function was going up and when it was going down. And what I mean by that is as you go to the left, right? So if I start from negative numbers, and I'm sorry, as you go to the right. So I start from negative numbers and move to the right. So I get bigger and bigger and bigger and bigger and bigger. What happens to the graph of the function? If it's going up, we say that it's increasing. And as we go to the right, if it's going down, we say that it's decreasing, right? So again, here would be the increase. Here would be an increase, and then in between, it's a decrease. So here it'd be decreasing between -2 and 2, right? That's the region or the interval of decrease. And if we were to compute the average rate of change for any 2 values in between -2 and 2, for example, if I were to pick -1 and 1, we'd see it would have a slope that was negative, okay? If I were to, for example, pick 3 and 4, I'd have a slope that was positive for my average rate of change. And so the average rate of change is telling you when the graph is going up and when the graph is going down. The larger the number is, the more vertical it's changes, right? So the more change it's undergoing. So this is the idea of increasing and decreasing. And the cool thing with increase and decrease is you can start to begin to see where the maximum value of a function is. Because the maximum value in this region over here, this is called a local maximum, is the place where the function goes from increasing and then it starts to decrease, right? Because this is the biggest it'll ever get, increasing to decreasing. So here we have a local maximum of 16. It's not the biggest value of the function because over here it gets bigger than 20. But if we were to sort of stick to this small region here, we have a hump, and so we would call that a local maximum. This guy over here is a local minimum, and we want to think about the y values, okay? So in that case, that local minimum would be down there at -16. So we have local minimums and local maximums, increasing and decreasing. And the increase and decrease, we do the same way that we did for domains. We list it out in interval notation. Okay, so this is that same picture again. Here we're increasing up to this point right here, and then we're decreasing until we hit this point here, and then we start to increase again. And the cool thing about these 2 points is, again, this one's called a local maximum. The local maximum itself is 16. Be careful on infinity how they're asking you these questions. Sometimes they'll ask you what is the local maximum, and then other times they'll ask you where it occurs. And sometimes they'll ask you both, right? And here, where it occurs is at x is equal to -2. So they're asking for what's the input value where the maximum occurs. In this case, the local maximum. Because there's values that are bigger, right? Like over here, I get past 20. So this is even bigger on, if I plug in 4 or 5 or something like that. But here I have a local maximum. And then over here, I have a local minimum. And the y value, like we said before, was -16. So there we would say it's a local minimum. And you can always figure them out because they happen basically at places where you change from increasing to decreasing. That's the max. Decreasing to increasing, that's a min. Okay, so what do we mean then by an absolute maximum and an absolute minimum? Well, an absolute maximum and an absolute minimum is a y value that is, in the case of a maximum, larger than any other y value on the graph. Okay, so it's not local, but absolute. Everywhere it's the biggest, okay? And a minimum is a y value that's smaller than any other point on the graph. So here we have this nice function. The domain is from -1 all the way to 2, right? So the domain is the x values. So our domain is -1 to 2. And the smallest y value that ever occurs is 2. I'm sorry, -2. And the largest y value that occurs is 2. And there's nothing else that's smaller, and there's nothing else that's larger. So we would say that the absolute maximum is 2, and it occurs at x is equal to 2. And the absolute minimum is -2, and it occurs at x is equal to 0. So affinity will ask you to look at graphs and identify the local mins and maxes, and then also identify the absolute min and max. So let's end with an example here of a function. And what we would like to do is find all of the pieces we've been talking about. So let's find the domain. Let's find the range. And let's think about the local maximums, the local minimums, the absolute max, and the absolute min, and where those occur, okay? So let's think about the domain. Let's think about the range. Let's think about the local maxes and the local mins. And then again, the last thing we'll talk about is what's the absolute max and what's the absolute min. And they may not exist, right? If your graph just goes on forever, going bigger and bigger and bigger, there may not be an absolute max nor an absolute min. Okay, so here, what's my domain? Tell me what I get from my domain. What are the x values that intersect this graph? Be a bit careful about where this starts, too. Gotta drop down to here. So yeah, it starts there at -2.5. And the last value that's defined is over here at 3. Okay, so we go all the way to 3. So that's the domain of this guy, right? Let's think about the range now. So let's come back and look at the range. What do the y values range between? So the smallest y value is over here, and the largest y value is up here. Okay, and we're halfway between -8 and -12, so that's certainly there at what? Okay, so -10. Okay, so we're going from -10 all the way up to 16, and we include both of them because we reach both of those values. And you'll notice that this sort of tells us immediately what the absolute max and min is, right? Because the absolute max, the absolute min, I mean, it's really told to us by the range, right? So the absolute maximum is 16, and the absolute minimum is -10. Those are the absolute min and max. Now, where they occur, we have to be careful about, right? Because the question may be asking us, sorry. Okay, technical issue here. See if we can get the graph back up. Okay, there's the graph. So the place where they occur is the maximum occurs at -2 and 2, right? That's where you hit 16. And the minimum occurs at 3. Okay, so the local maximums are the same thing as the absolute maxes here. So the local maxes are over there at 16 as well. But what is the local minimum? So there's a local minimum that's not an absolute minimum. What would it be? There's a local minimum that's not an absolute minimum. Yeah, it's at 0, right? It's that bottom little piece there. It's not the absolute minimum, but it's definitely a local minimum of 0, and it occurs at x is equal to 0, right? Where those other two occur at -2 and 2. So here's what the answers would look like, right? So the local max is 16. There's 2 of them, one at -2 and one at 3. I'm sorry, one at -2 and one at 2. The local minimum occurs at 0, and it's at x equals 0. The absolute minimum is -10. The absolute maximum is 16. And here's our domain in our range. Okay, and I'm 2 minutes over, so I need to stop. But that was basically everything that we had in this one, everything that we really wanted to cover. And that goes through all of these learning objectives, okay? Okay, and actually, these are the wrong learning objectives, so I apologize. This should be the ones at the beginning. But I'm going to stop the recording.